Hello again. Today we are going to go over the last half of the nucleophilicity versus basicity handout, and we'll talk about some important trends. And we have talked about some of this previously, but we'll just go back over it again. So let's dive in here. So last time we talked about the main differences between nucleophiles and bases. So we said bases are going to grab onto a proton, whereas nucleophiles are going to attack something other than a hydrogen, like a carbon. We also talked about how nucleophiles have more to do with kinetics, so reaction rates and how quickly a reaction occurs, whereas bases have more to do with how stable the products are. So let's relate this back to what we were discussing last week. So last week we talked about how nucleophiles are better if their electronegativity is smaller. Or another way to phrase that is nucleophilicity decreases as electronegativity increases. So the main idea is that if something is less electronegative, it's a better nucleophile. And previously we had compared H2O versus NH3, which are both neutral molecules, but they both have lone pairs that they can donate. And we said that H2O has an oxygen atom, which is more electronegative, so it's going to hold on to its lone pairs a little more tightly than nitrogen, which is less electronegative. So we said that NH3 was the better nucleophile because it's less electronegative and therefore is not going to hold on to its lone pair as tightly. Now, this is also true with bases. So basicity also decreases as electronegativity increases. So if something is less electronegative, it's a better base. And it's really for the same reason, because if we compare, for instance, OH minus or NH2 minus, oxygen is more electronegative again, so it holds on to its negative charge or its extra electron more tightly, versus NH2 minus, where nitrogen is less electronegative, so it doesn't hold on to its electrons as tightly, and it can react more readily, or grab onto a proton more easily. So that's also the same as our nucleophilicity trend. So why are these two trends the same? Because atoms having higher electronegativity can stabilize lone pairs better than atoms having lower electronegativity. And this is true for both nucleophiles and bases. Okay, so now what if we're comparing nucleophiles or bases that have atoms in the same column? So what we just talked about was referring to nucleophiles and bases that have atoms in the same row. So oxygen and nitrogen are in the same row. But what about if we're comparing, let's say, oxygen and sulfur, which are in the same column? Well, we're no longer going to think about electronegativity as much. We're thinking more about what type of solvent we're using. So we talked about that last week. But we're also thinking about things like atomic radius, as well as, well, I already said the solvent. So let's kind of scroll down here. So in a column of the periodic table, in a protic solvent, the nucleophilicity of anions increases as atomic radius increases. So if we're comparing OH minus and SH minus, we're no longer thinking about electronegativity, we're thinking about the size of the atoms. So remember, as you go down a column, atomic size increases. So if we compare oxygen and sulfur, sulfur is a lot larger than oxygen. So sulfur, because it's larger, is actually going to be less solvated than oxygen. And in a protic solvent, that's important. So let's see, let me choose a different highlighter here. Let's do green. Because protic solvents tightly solvate small anions. So if you have a larger anion, those are less tightly solvated by protic solvents, and they're more able to attack. So SH minus would be the better nucleophile in this protic solvent because it's more able to kind of break free of the solvent and attack a carbon, for instance. Now, what about if we have an aprotic solvent? So something that doesn't have a hydrogen attached, it's just polar. So it can't hydrogen bond, remember. So in an aprotic solvent, the nucleophilicity of anions decreases as atomic radius increases. So this is opposite of what we just said for protic solvents. So if we're comparing, for instance, SH minus and OH minus again, this time in an aprotic solvent, the oxygen wins in this case. So that would be the better nucleophile. And the reasoning is because aprotic solvents solvate both small and large anions equally poorly. So what we care about more here is what is the better base. So the better base is also the better nucleophile. And if we go down to part D below, the better base is going to be the smaller ion. So basicity always increases as atomic radius decreases. So for instance, if we're comparing iodide to fluoride, fluoride is the better base because it's smaller. Okay, so why? Why is fluoride the better base? Because it's smaller. Well, let's go into a little more detail. Smaller sized atoms have better orbital overlap with the small 1s orbital on hydrogen. All right, now also the larger orbitals on larger atoms reduce electron-electron repulsion and are thus better stabilize an anion. Okay, so let's also talk about C, and then we'll kind of summarize everything in our PowerPoint slides because I know this is a lot of information. So it's kind of hard to keep track of what's going on. All right, so in both protic and aprotic solvents, the nucleophilicity of neutral molecules increases as atomic radius increases. So for instance, if we're comparing H2O versus H2S, neutral molecules are not as tightly solvated as anions because they're neutral, so they don't have a charge. So if you have a neutral molecule, we care more about what's called the polarizability. So how spread out are the electrons? So the more polarizable nucleophile attacks more quickly. So sulfur is our larger um, atom. So sulfur is going to, or H2S is going to be our better nucleophile in this case because its lone pairs are more spread out. Um, so it's not holding on to, uh, or it doesn't have a concentrated set of electrons. So it's more able to attack. All right, so let's summarize all this into some PowerPoint slides here. So let's find the right slide. Okay. So let's talk about nucleophile strength, and we'll also talk about basicity strength as well. And we're going to compare, again, atoms that are in the same column. So let's just pick a few. Let's say we have OH minus versus SH minus, and we'll add one more, let's say selenium. So these are all in the same column, in column 6A on the periodic table. And the atomic radius is increasing as we go down. And let's say that these are all in a polar protic solvent. So that would be something like H2O, or maybe we have, for instance, methanol or ethanol. So there's a hydrogen bonded to a very electronegative atom. So these can hydrogen bond. Now, remember, hydrogen bonding only occurs if you have a hydrogen between two very electronegative atoms. So hydrogen bonding is going to increase going up because oxygen is very electronegative. So H bonding increases going up. And in fact, SH and SEH would not be able to hydrogen bond. So they would not be as tightly bound by the solvent, right? However, OH minus would be tightly bound by the solvent because it can hydrogen bond. So we can even write here more solvated as we go up. Okay, so now let's talk about nucleophile strength. So nucleophile strength is going to increase going down the column because, again, remember, those atoms that are further down the column are less tightly held by the solvent, so they're less solvated. Okay, now they're less solvated not only because the hydrogen bonding decreases going down a column, but additionally the size of the atom is increasing. So it's less likely to be held tightly by the solvent. Okay, now what about bases? So the base strength is actually going to be opposite for um, for this case because remember, all we care about with bases is the atomic radius. Okay. And in this case, most likely the base will take a hydrogen from the solvent, for instance. So it kind of depends on the reaction you're doing there. Okay, so just to summarize, in a polar protic solvent, the nucleophile gets stronger down a column. Okay, so hopefully this chart helps a little bit with summarizing some of that information we went over. Let's also compare nucleophile strength in a polar aprotic solvent. So we're going to compare the same three nucleophiles, but this time they're going to be in a polar aprotic solvent. So this would be something like acetone, where it's a polar molecule, but it doesn't have any hydrogen bonding. Now, again, remember that atomic radius is still increasing as we go down. And in this case, there's no hydrogen bonding again, so the polar aprotic solvent it's not doing a great job of solvating these ions. It equally solvates these ions in the sense that it doesn't have any hydrogen bonding. However, remember that the size of the atom is important. So in this case, the nucleophile strength is going to be the same as the basicity strength. So nucleophile strength increases going up the column they're all equally solvated, poorly solvated, I should say. So I'm going to change that. They're equally poorly solvated. So this depends more on size. And we said that basicity strength increases for smaller atoms. Okay, so overall, in polar aprotic solvents, nucleophiles get stronger up a column, similar to bases. And again, the reason why basicity strength increases for smaller atoms is just due to the fact that the orbitals are smaller, so there's better orbital overlap with a proton, because protons are really small as well. And in this case, the nucleophile strength will just follow the basicity strength. So it just really depends on the size in this case. All right, and then what about neutral nucleophiles? So let's say we're comparing ethanol to a similar nucleophile, but we've just switched out the oxygen for sulfur. So how do these compare? So the OH on ethanol can hydrogen bond, because remember, oxygen is a very electronegative atom. But the sulfur and hydrogen on our other nucleophile cannot hydrogen bond. So that means that ethanol will be more tightly packed in the solvent. So we could also say more solvated. And our other nucleophile is not as solvated. So let's look at ethanol. This is actually going to be less nucleophilic due to the fact that it is so tightly solvated, it won't be able to attack anything. Whereas our other nucleophile is more nucleophilic because it's not as tightly solvated. And this is true in both types of solvents. For both polar solvents, the nucleophile gets stronger down a column. Okay. So in the next video, what we'll do is we will look at an example of an SN1 reaction. And we'll talk about how the solvent can actually act as the nucleophile. And then we'll sort of summarize our nucleophilic strength a little bit further. Because I know I threw a lot of information at you, so I just want you to take a minute to absorb this information, and then we'll use it in the next video.